Hello guys, I hope you feel great today. Let's start with the topic of variance. So for this, I have three different questions or examples to explain you how is the best way to select variance with calculation. So something that we have to remember it's about this picture that is in Spanish, but well, I think we understand it just looking it. As you can see, this is an example for radial load, axial load, and combined loads. So this is, imagine this is the shaft and well, the rotor of the electric motor, and this is the weight of that rotor, and you're gonna have two different forces in the y direction. So in this case is radial load, the first picture. So let's start with the first question or our first example. It says select smaller deep groove ball bearing that can support a load. This is a radial load, 5,250 at 1,000 RPM. The bearing life should reach 20,000 operating hours. So for this, I have three different examples for each question. So as you can see, this is an example. So what is the best bearing for this case with this condition? I'm gonna well there's a in the SKF page you can download the all the this you can download all these files PDF. This is in Spanish, but I'm gonna explain you each one, and we're gonna use all this information. As you can see, this is more than 1,000 pages, so that's the reason why I divided this in all the information that we're gonna need. Something is, as you should know, these are loads or conditions that you're gonna need. So that's maybe if you don't know the how operational you're gonna need, but that's an example. Um, this there's an example. This is an instruction of well, this is in Spanish we do service life of the bearings. This for your house machines. So it's small. You have mixer more than over than 8 hours. Uh, so this is something if you want to have an idea. It's for years. For some compressors, as you can see, pumps. Um, well, this is for the transmission, a generator. So there's a lot of options that you can select. So for this example, we are here for, let's check. All we are gonna need is this, and to understand these two equations that is gonna happen. Our first equation is for our service life by working. This is for working hours. So this is the reliability coefficient. This is the SKF coefficient. This is the P is equivalent load. It's the dynamic load, and and this P is a bearing time factor. So it's what we have here. So something that we have to chart. It's about the equivalent load. This is for here. And this is we have two different ways to how to calculate this. So as you can see, this is for axial load and this is the radial load. Where this number is less or equal than this value p. This is about a table that we're gonna see on the PDF where I have an extract, as you can see here. We are the the equivalent load it's gonna equal to radial load, but it's in the different case. we're gonna have to do a different calculation. Why I'm gonna use the first? Because if you read, there's no absolute, so it's like just small, maybe. So this number is gonna be 0, maybe 0 point something. So all of this is gonna be the relative. So let's start with the first. We have 1,000 RPM, and this is Newton, and we need kilonewtons. And there's 1,000, and we need 5,000.25. Okay, this is live working hours. So that's the information that we have here. 20,000 and 2, 3. And maybe your first question is, how do you calculate this? These 4 millions of revolutions. So there's a factor to change it of the SKF down left here. How to convert this number to this. So you can see we have in hours and we need in millions of revolutions. So it's like a free rule. And is for the speed RPM. So our revolution. So we are going to multiply it. And as you can see is this. It's in life in hours multiplied with 1,000, the RPM 60, and divided by 6 times 10. So now we have the life in millions of revolutions. And for this, we need we're gonna calculate the dynamic load. I'm gonna explain you why. Something more that we need to check is the SKF coefficient. And something important we have to remember here. It's like a life adjustment maybe of service. But this is a table also fits with ASKF. With ASKF, you should match the information. This is something that we're gonna see in the second example. Well, in this case, as you can see, K is something different, and you should match like a vertical line and then a horizontal line to know why the more approximately ASKF coefficient. So something that you have to know, as you can see the equation, it's like you should know the nominal bearing, maybe something like. So for in these cases, if you only have to know what is the best option, the first option, because you could have more. So the first option, you always said when you're gonna have to select, just put 1 here. This is like a nominal. You have to only something that you want to know what is the best option. Not the best option, the first option maybe. Just put 1 and then play with the numbers. But you should check it. That I'm gonna explain you with a second example. Let's continue step by step. Just take that information. In this case, a probability coefficient. So you should know something. You can see for this, there's a table of what you have since 90 until 99. So what coefficient should we select for this? Well, sorry. Okay. Well, for this, you should only should know because we are gonna select the first option. So this reliability, it's like a maintenance factor that we gonna see in a video in the future. But you only should know the first. If you are looking this information with the reliability of service life, just select the less percentage of this, 90%, because you have to know maybe the, gets in quotes the bad option. It's not really the better option, but let's take that word. So 90% it's gonna have a third uh, reliability coefficient. So let's put 1. In this case of bearing type factor, let's something it's here. When it's when it's uh how can I say it? When it's a deep group bond, it's gonna be 3. And which it's bearing with just give me a second. When it's mm, okay, when it's a roller bearing, it's gonna be this 10 divided in 3. So here, for us, for this sample is 3. And what we are gonna do here, we just multiply this two coefficients divided if they're in the surface medium of revolution. Um, we are in this case one of the roots of this number and then multiplied by the equivalent load. So that's we are gonna make it here. It's well, as you can see, just calculating the dynamic load. So it's mathematics. So this is for okay, this is in kilonewton. So what we're gonna do in this with this step, so now we should check all the 5 of type of bearings. So we're in this it's 55 79 newton. So let's check in all the type of bearings what bearing can support that force, that radial force. So let's check, and as you can see, you're gonna see something like this. Wait, let's search the deep groove ball bearing. Okay, here you're gonna have. Let's see that information. This is dynamic load C. So as you can see, it's in kilonewtons, and you should have a bearing that can support 55, 79, or 56 if you're. So if you can see, this is 54. So now we don't need that bearings, and you should search something like that. This is 50, 63.7. It's too much. So let's check 55.3. No, almost, but no. So that's how you should search it. So look here. What is the first option? Okay, here. Since here. No, too low. No, no, no. No, no, no. Let's look here. Look, we have the answer here. We need 55, 79, but we have 63.7. So as we can see, 52 is no. So our first option should be this 6,408. This is the bearing that we need. So let's do this. Our answer is 6,408. So this is the type of bearing that we need. Okay. So okay, this is the first example. Now let's look second question. SKF bearing 6008 is installed in a gear transmission and lubricated with an oil of viscosity equal to 68 square millimeter per second. Assuming that it works under a radial load of 3.5 kN and an axial load of 1.6 kN at 1500 RPM and a temperature of 70 degrees Celsius and an environment with good cleanliness. Determine the adjustment extended bearing life in hours with a reliability of 95. So here we have too much information, and we are going to use to, as you can see, determine the service life in this case. Now we know the bearing, and now we want to know, or we would like to know, how many hours in this bearing going to have in service. So for this, we have these different Excel, and we are going to compare. That's the reason why it's two. It's the same. We are going to compare some values. So the first we should know is the bearing. So you can see it's 6008. So let's start step by step. It's here. This is the information that we have. And as you can see, we have these units: dynamic load, static load, fatigue load, calculation factor, axial load, radial load. So it's not calculation here, not any equation for this. We should only know the values. You can see dynamic load is gonna be 17.8. So let's put 17.8. Static load 11. Fatigue load 0.49. And this 11, 0.49. Calculation factor F0 is gonna be here. As you can see, 6008 variant is in the fourth position. So let's get the next page. You're gonna see the next data that you need for here. So it is 15 for 6008. So 15. Axial load is the data that we have. 1.8 for axial and 3.5 for radial load. Okay, it's in kilonewton. So let's check this information. We're gonna close it. So the first equation that we have is you should know the axial load divided with the radial load, and this is like how can I say it? Enter value, beginning value maybe. This doesn't have a number where we are gonna need it. This is just multiplied, well, this number with the calculation factor. No more. Okay? Same. Divided with the static load. So let's check this information. Why? Because we need to know the dynamic load. And in the case for dynamic load, we should check this. As you remembered, so we need this equation. We now have this, but we should know what is the value of E. So I have this part of the fight here. This is for deep groove bearing. Here, that's the reason why I told you we are gonna need this information. So as you can see, we have 2.182. So we are here in this range. We should make an interpolation for this. For x, no, it's not needed because it's the same. And for y, yes, we are gonna need it. So it's 2.07 and 3.45. Also, as you can see, I have here with the Spanish video. For E, we have 0.34 and 0.38. 0.34 and 0.38. So our interpolation is 0.3432. So for our value, it's gonna be 0.3432. So as you can see, you should check this value with this value. Our number it's a little bit bigger than E. So we should to make the second example. So now we need an X value. It's 0.56. But why we have to make another interpolation. So 1.31 and 1.15. So now the value is 1.29. I wish you all three decimals. Okay. So now we have the equivalent, and as you can see, it's we are using this normal. It's the x with the radial loop plus y multiplied with the axial load. That's the information. Now for the bearing, for the data of the bearing, we don't need this. We were here. Search it again. It's the bearing type of this. Let's make the PDF make the work. Okay, it's here. This is the internal diameter and this is the external. So 40 and 68. So it's 40 and 68 in millimeters. So this is our value that we're gonna have for more. We're gonna need that. This is like just 0.5 multiplied with the plus of this. This is the medium diameter, maybe. Let's call it in that way. RPM. So this is an information 1500 RPM. For this case, let's check it. Let's check it for viscosity. I know we have this information here, but I'm gonna explain you if you don't know it how to select it. So the more we're gonna need this part. Okay, what for this? What information we should need? So what should we need for this? You have some data here with in this case for 40 degrees if you don't know, but if you want select you should make this information, and as you can see that's the reason why I told you we're gonna need the medial diameter maybe with the RPM. So here if you know it's your first time you see this kind of graphic of diagram maybe you just should make a match of what this is for my another example here. Okay. And for us, our value is 1554. So we are almost here in margin. 55 is here. Here. So this is you should know this is our value because you should try to make a value in this range. It's not 15 as you can see. So, but we are gonna try to put this just to make simple in the middle maybe. Our temperature for us is an information of 70. This is here. This is our value. Okay, here. And oil, and for us in this case, we should save the match here. This is the same. We should enter with the oil value, with our temperature, and with our viscosity. So let's look. Let's delete it. Okay. Here we have 70. Oh, okay, we were here. And we have viscosity of we have 70, the viscosity of 15. So we are almost here. Imagine we are here, almost here. Okay, here. So you should always select the next one, not the most closed, the next one in this case. If we were here, for us, our answer should be 32, but we are here, almost here. So for us, our selection should be 46. Is 6. So now we are going to have this value of k. This is just a equation of the viscosity divided with the oil ice. So now we should know this cleaning for this cleaning factor maybe. So for this information we should just there's another part of the file. Let's check. This is our factor that you should know. So for us, first information that we need is the external diameter. So it's 68. So for, as you can see, okay, no, this is the medium diameter, 54. So it's less than 100. So not here, we are here. Some information for this example, you should use your own case, but this is for this example, that it's an environment with good cleanliness. So we are here. So maybe in our second option with good cleanliness, I'm gonna use 0.8, but you can put the value you want in the case you are. So don't worry, I'm gonna put 0.8. I'm gonna have this value. With this value, we are gonna, as you remember, this is to select the SKF coefficient. So let's close this. Now we are gonna have this. We need this value. So something that we already know for the example, it's 95 of reliability. Reliability, yes. So this is a data. It's not weird. It's not nothing here. Okay, but the value for 95 it's 0.64 for in the case of reliability factor. So 0.54 we need. Now for the SKF coefficient, we were here. This is for this group ball bearing because there's also for roller bearing. In the case roller bearing, and you have for axial load. This is for radial load. Radial, and this is for axial. So you should consider that information. So let's select. As you can see, that's the equation that we need. So that's the reason why I told you that. Let's wait a little bit. I'm gonna take the screenshot of this. This is the second option for Explorer bearing, but just in case you have it. If you have all the different or other bearings, so let's use the information. So we don't need this. Let's change it. Behind this. Okay. Okay. This is our enter value. As you can see 0.09. So we are here. We are almost here. 0.09 maybe. Here. And for K, we have 3.076703. It's almost here. Okay. What value should we put in case of here? Because we are in the range of 5 until 10. So I'm gonna use 6 maybe. So okay. Now let's wait. We need the bearing type factor. So see, we are in the case of ball bearing 0.6008. Yeah, 2008, it's a ball bearing, as you can see. So if you remember this example, it's the same. It's not a roller bearing. For ball bearing, the bearing type factor, it's going to be 3. So now we calculating the life median of revolution with 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 this equation. I'm gonna put the value the same. As you can see, we have C. Now we have the equivalent load in different. P for the bearing type factor, it's gonna be 3. The reliability coefficient 0.64 in case of 95%. And our SKF value is 6. So now we have the in million of revolution. If we want in hours, but you should make just like the last case, but now in a different order. So let's check it. Now we have in million of revolutions this, and we know in hours. So it's just a difference. The only difference of the last example is now we are working with a different RPM here. We are different with a different RPM and with a different equivalent load calculation. So for us, it's gonna be 3062, 662 service working hours. And maybe you are asking why we have another table with almost same information. Because now for this example we're using the viscosity of that bearing. But remember, if you don't have maybe experience for feed service, don't worry. But maybe you know that this all for transmission maybe could be a little bit less this viscosity, sorry, so we need more. So for our example, we have 68. So let's look how this 68 all viscosity is gonna change all the result for us. So for this, it's the same. It's the same. We are gonna copy this. Okay, say it changes here. We now have 68 with a temperature of this is the same temperature. So now let's look this. So this is something different we not need. Okay. So here viscosity table. So let's change it. Now it's different. We don't need this because now we have the viscosity, so we don't need this. We need to know K. So for us it's 70. 70. Imagine we have a line here. We have 70 and a viscosity of 68. So we are I'm gonna take the picture and say okay, we are here. Okay, no. Here. We have 70 degrees. It's the same, but with a viscosity of 68. So maybe here. So imagine. So as you remember, we should select the next one. So 320. So for us now, our old ISO is 320. And our K is that we have a different value for K, 4.7. So now we should select our cleaning. Well, our value for the cleaning table is going to be the same. It's not changed. But now we have a different answer value for the ASKF coefficient. The reliability is the same, so I'm just gonna copy the same value. I'm sorry, 95. The bearing type factor the same. So now we only need the SKF factor that it's different. So for us, we should add it here. for a ball bearing in radial load. So we know that there's combined, but don't worry, because it's a ball bearing. So here, we are here, and as you can see, we should a different enter value when with the enter value it's here. 0.1. This is the same, almost the same, but our K is different because we have 4.7, but we're almost here. Use the 4 curve. I'm not inventing anything. It's almost here. If K is bigger than 4, use the curve of K equals 4. So I'm just doing that. But we are in this range, so I'm gonna put almost this maybe because we're in the same. Oh, let's check it. 768. Okay. It's the same value over here. 68. We have a different temperature here. SKF. Oh, sorry. The problem is here. And as you can see, we are in 4. So let's try to put a little bit, maybe 7 point. I don't know. It's not 8, but it's not 7. I don't know. I'm gonna put 70. This maybe. Well, I don't know. Just a little bit because 3 in our last example were here, almost here. So now try to put a little bit more. So 70.5. So now as you can see, we have two different results. If you're in first in this with the table viscosity for that bearing, if you don't know it, but if you know that the bearing for transmission, maybe you should now if in first degree you know that we have a different viscosity for that transmission, not only for the bearing, just more for the years. So in the future video, I'm gonna explain you how to select the best oil for the transmission. But with here, you should just look at that bearing. So for this example, if you don't know the viscosity and you see the SKF told you, we are gonna have a 3,662 service working hours. But now you know it's 68 viscosity. As you can see, we're gonna use 320 ISO. So don't worry. Now we are gonna have 5,578 service working hours. So let's put this. Okay, here. The adjustment extended bearing life in hours. So we're gonna have 3,662 hours for 46 squared millimeters per second. Right? Or maybe we can put the ISO. Yes. Okay. I'm gonna use this. And this is seventh, no, 578 hours, 68. Square millimeter. Okay, but it's the same information that I'm gonna put in this. So just try to put it. Check to use the same, or maybe. Okay. So now let's with the third question. This regarding the last case, calculate the nominal duration in operation hours that the bearing can reach Calculate the nominal duration in operand. Oh, okay, this is the time, sorry. So, as you remember in our first example, there's something that I told you for nominal case. It's with ASKF, it equals 1. So, it's going to be the same value. I'm going to put this. As you can see, dynamic load, static load, calculation, axial load. It's the same. So let's put this. Our E value table is the same. It's the same. I just copy the same information. As you can see, our equivalent load is the same because we are in the same case. The difference is here. SKF coefficient for nominal case, we only want to know what is the nominal case of bearing. That means with a lubricating case, it's no oil, it's no distribution of loads, there's nothing, just a bearing. It's not a good environment, you don't know the temperature, maybe just that bearing for nominal case. So with this, you should put now. Reliability, as you know, there is the same of the last. This is 0.64, if I remembered. Okay. Bearing type factor is a ball bearing, so that's the reason why we are gonna using 3. Service million of revolution is the same equation that we have here. It's the same. It's the same. Now the RPM is a different position, but we have 1500. So as you can see, our with the conversion just net. So as you can see, our service working hours is gonna be 610 hours, service hours, just for the same bearing in the same case, but we are just with a nominal duration. So our answer is gonna be 610 hours. Look the difference. So that's the reason why in maintenance there's always something that you should know. Let's lubricate in this. That maybe you use the bearing type of 2C that doesn't need more lubrication. So there's a lot of, or 2Z and 2RS. Uh, both of these don't need lubrication because it's covered. It's the lubrication of that bearing is for an entire life. So, but this is an example. Okay, if you wanna compare what is gonna be the best option for you, if you only wanna know in the maybe the bad case, the a lot of rust condition or too much load, too much vibration, what is the nominal duration of that bearing is gonna be on, please. So, but if you have one different condition, it's gonna be different. So I hope you this free example with this free question maybe help you to understand what is the best way to select that bearing, select what it, as you can see in the second example, select what oil maybe you need for this, what is the best option for you, how to save money, how is the best bearing to for in case of different loads, radial loads or axial load. Imagine that you have the motor of, let's look this. Imagine that you have this, but in oh, no. Imagine that you have this. Okay, but in an axial position. So you should check this bearing. You should check this bearing. This a little. Imagine that we have here the brake of the motor maybe. But now you should check this bearing because now we have all this weight. We're gonna we are in a different case, the axial load. That for this case we need this type of bearing, maybe roller bearing or what for this. of ungood contact pairing, maybe this kind of pairing. So I hope you this information helped you. And if you have any question, please do not hesitate to do it. Just do it. Put in the comments to help you. And I hope you have a really fine day, a really great day. Let's look at the next week. Our next video is gonna be in Spanish, and the next of the next week it's gonna be on English. So I hope you really fine great today. Thanks for your time.